The next chapter is instruments. The first instrument is direct ophthalmoscope. The direct ophthalmoscope is commonly used for routine examination of the fundus of the eye, especially when a slit lamp cannot be used. It is small, easily portable, and can also be used to examine the more interior parts of the eye. It is important, therefore, to understand how it works and its advantages and limitations. The instrument consists of a system of lenses which focus light from an electric bulb. These are the lenses. These lenses focus the light from an electric bulb onto a mirror. So this is a mirror inclined at 45 degrees, where a real image of the bulb filament is formed. The mirror reflects the emitted light in a diverging beam. This is a diverging beam which is used to illuminate the patient's eye. This is the patient's eye. The mirror contains a hole. This is a hole in the mirror through which the observer views. This is the observer. The observer views the illuminated eye. The image of the bulb. This is the bulb. The image of the bulb is formed just below the hole. This is the hole, so that its corneal reflection does not lie in the visual axis of the observer. So that's why the image of the bulb is formed just below the hole, so that its corneal reflection does not lie in the visual axis of the observer. The area of retina which can be seen at any time is called the field of view. It is governed by the projected image of the sight hole on the retina, the sight hole being the hole in the mirror or the observer pupil, whichever is the smaller. So this is the sight hole. The image of the sight hole is constructed using a ray through the nodal point N and a ray parallel to the visual axis, which is refracted by the eye to pass through its posterior focal point. The field of view is smaller in a myopic patient, and it is larger in a hypermetropic patient than in emmetropic eye. So the field of view is smaller in a myopic patient. The field of view is considerably enlarged when the patient pupil is dilated. Hence the advantages of installing a mydriatic prior to fundoscopy. The field of view becomes larger as the distance between the patient and the observer is decreased. So in order to utilize the maximum available field of view, so it is necessary for the observer to be as close as possible to the patient's eye. Because the real image of the bulb lies just below the sight hole, the field of view is not evenly illuminated. A dark shadow that is often seen when the peripheral parts of the retina are examined is due to the total internal reflection of light at the periphery of crystalline lens. The image formed in the observer eye is inverted, so is seen as erect. The size of the image formed in the observer eye varies with the refractive status of the patient eye. So the size of the image depend upon the patient refraction. So the image will be smaller in hypermetropes and it will be larger in myopes. So in myopes, the image is larger and the field of view is smaller. So the field of view is smaller in a myopic patient, while the image is larger in myopes. Small field of view and large image. Now when the observer is emmetrope and the patient is also emmetrope, then the rays of light which leave the patient eye are parallel and they are focused on the observer retina without any accommodative effort or the use of correcting lens. Now if the patient is either myopic or hypermetropic, Then there are correcting lenses. These are the correcting lenses. This is the lens wheel. We should select according to the patient's refraction. If the patient is myopic, then convex lenses are used to see the fundus of the patient, and if the patient is hypermetrope, then concave lenses are used to see the fundus of patient. So in this case, this is concave lens, so it means that the patient is hypermetrope, so converging rays are emitted from the patient eye, so which will be diverged by this concave compensation lenses, and vice versa in case of myopic patient. As we already told that in case of hypermetropia, the image seen by the observer is smaller. In case of myopia, it is larger. The use of correcting lens also reduces this discrepancy in size. So again, for hypermetropic eyes, small image, wide field of view, whole fundus can be scanned quickly. Myopic eyes, large image, reduced field of view. So now to mention that in axial myopia, the eye itself is bigger than in emetrope eye. So it is difficult to examine a myopic fundus using the direct ophthalmoscope because the large image coupled with reduced field of view. So if you want to see the posterior pole of a highly myopic fundus, it is best seen with the direct ophthalmoscope if the patient keeps his glasses on. Now what about astigmatic eye? we can only use the correcting lenses. The correcting lenses are spherical in direct ophthalmoscope, so we can only use spherical correcting lenses. There are no cylindrical lenses. So in case of astigmatic eye, it is impossible to secure a perfect view of the fundus, and this only possible to correct one meridian at a time. So if the degree of astigmatism is high, the difference in image size due to the disparity of the dioptric power of the eye in the two principal meridians cause distortion of the image and the optic disc appear oval. Now what about the refractive status of the observers if the observer have refractive error? Now there are two possibilities. The observer can remove his spectacles and rake up the appropriate lens in the ophthalmoscope to give a clear view of the patient's fundus, and that appropriate lens is the algebraic sum of his own and the patient's refractive error. So for example, if the patient has +2 refractive error and the observer has also +2, so then he must select +4 to see the fundus clearly. If the observer has -2 refractive error and the patient has +2, then there is no need to use any correcting lens. Alternatively, he can use the instrument with his glasses on. However, his field of view will be restricted because the field of view becomes reduced as the distance between the patient and the observers increases. So the first option is good than the second one. Now what about the magnification of the patient's retina when viewed through the direct ophthalmoscope? The formula is f divided by 4. So if we ascribe our dioptric power of 60 to the patient emetrope eye, so put 60 in place of f, and 60 divided by 4, so the magnification of direct ophthalmoscope is 15 times. This degree of magnification makes the direct ophthalmoscope particularly useful when examining patients with retinopathy, for it allows most microaneurysm to be seen. Many modern direct ophthalmoscope incorporate a red-free filter, so the microaneurysms appear as black dots against a green background, and this makes their detection easier. Now, how to see the interior segment of the eye, such as lens opacities? So it can be inspected through a +10 diopter correcting lens. So select +10 and watch the interior segment. Enjoy. So this was all about the direct ophthalmoscope. Now we will go to the indirect ophthalmoscope. Hope you will enjoy it. Now let's talk about the indirect ophthalmoscope. It offers an alternative mean of examining the retina. Here you can see and vitreous, and gives a very different view of the retina compared with that obtained with the direct ophthalmoscope. Both instruments have their place and should be used to complement each other during clinical examination of the eye. And this is the table which sets out the characteristics of the two instruments. So the differences are in the image. The image in direct is not inverted, while in indirect it is inverted, both vertically and horizontally inverted. And the next difference is in the field of view. The direct ophthalmoscope view is 6 degree, which is small, as compared to a large 25 degree field of view by indirect. Next difference is magnification. The magnification of direct, in case of direct, is 15 times. In case of indirect, it may be 3 times or 5 times. 3 times in case of 20 diopter, 5 times in case of 13 diopter. Binocularity not available in direct. Stereoscopic view in indirect. Influence of patient's refractive error. Large influence indirect and small influence of refractive error on indirect. Teaching facility is not available in indirect and available in indirect. In indirect ophthalmoscope, a powerful convex lens. This is a powerful convex lens. From now on it will be called condensing lens. It is held in front of the patient eye. The usual powers are 20 diopter and 13 diopter. In case of 20 diopter, the magnification will be 3x. In case of 13 diopter, the magnification will be 5x. Illumination is usually provided by electric lamp here, mounted on the observer head. The illuminating light beam passes through the condensing lens into the eye, and the light reflected from the retina is refracted by condensing lens to form a real image here between the lens and the observer. This image is both vertically and laterally inverted. So it is situated at the second principal focus of the condensing lens, approximately 8 cm in front of the 13 diopter lens. The field of illumination is limited by the size of the subject pupil. The more dilated the subject pupil, the large field of illumination. So it is usual to dilate the patient's pupil widely prior to indirect ophthalmoscopy in order to widen the field of illumination. The field of illumination is also limited by the subject refractive status. So the field of illumination is largest in myopia and it is smallest in hyperopia. So this was field of illumination. Now the field of view, it is limited by the size of the observer pupil. Size of the observer pupil. Illumination depend on size of subject pupil. Field of view depend on the size of the observer pupil. So it is not practical to dilate the observer pupil because he would suffer an increase in aberration and loss of accommodation. And the field of view is limited by the aperture or size of the condensing lens. Large diameter lens, large field of view. Now the condensing lenses must be aspheric form to minimize aberrations. The linear magnification of the image can be calculated by this formula. Focal length of the lens divided by distance between nodal point and the retina of the subject eye. So if this distance is 15 mm, then the linear magnification will be equal to the focal length divided by 15. So if we use 13 diopter lens, so the focal length will be 75 mm divided by 15. So 75 divided by 15 will be equal to 5 times magnification. In case of 13 diopter lens, 5 times magnification. While the magnification of a 20 diopter lens, focal length is 50 millimeter, so the magnification will be approximately 3 times. Now the angular magnification of the image, it is equal to the dioptric power of the subject eye divided by the dioptric power of the condensing lens. So if the dioptric power of the subject eye, it is taken to be 60 diopter here, and the dioptric power of the condensing lens is 13 diopter. 60 divided by 13, it will be equal to 5 times angular magnification. In case of 20 diopter lens, it is almost 3 times. So it is obvious that refractive state of the patient eye affect the size of real image formed by the condensing lens. Now the refractive status of the patient's eye also affect the size and position of the real image formed by the condensing lens. So in case of emmetrope, the rays are parallel. So the real image is always located at the second principal focus of the condensing lens. In case of hyperope, the rays are divergent. So the real image is formed outside the second principal focus. In case of myope, the rays are convergent. So the real image is formed inside the second principal focus. Also in myope, the image size increases as the condensing lens is moved away from the eye. While in hypermetrope, the image becomes smaller. So the opposite happens in hypermetrope when the condensing lens is moved away. Now this effect can be used by the examiner to assess the refractive condition of the subject eye. So these are the different types of lenses used in indirect. In case of 20 diopter, the magnification is 2.97, field of view 46 degree. In case of 28 diopter, the angular magnification is 2.16 times, while the field of view is increased to 55 degree. 78 diopter, 0.87 magnification, 73 degree field of view. 90 diopter, 0.72 magnification, 69 field of view. Super field, 0.72 magnification, 120 degree field of view. So if one's need high magnification, then this 20D is and 13D are best. Now the merits, the relative merits of direct and indirect ophthalmoscope. Now the direct ophthalmoscope is much smaller and lighter than the indirect ophthalmoscope. The indirect are larger instruments with more powerful lights, so they are more useful in examining opacities in the ocular media. Also, the combination of good illumination, wide field of view makes the indirect ophthalmoscope the instrument of choice when examining the peripheral retina, patient with retinal detachment, malignancies. The indirect ophthalmoscope is also the ophthalmoscope of choice for use during retinal detachment surgery, because it is used at a distance which allows the surgeon to preserve a sterile operative field. Laser energy can be delivered through indirect ophthalmoscope to effect retinal photocoagulation.